Okay, so this is the new unit. It's unit 3, where we're going to focus on circular motion and gravitation. This is a shorter unit in the AP Physics world. Shouldn't take too long to get through some of these topics. Some of it's just a little bit of a review, especially when we apply such things as Newton's laws. But the first topic inside this field is something what we call a vector field. We talked briefly about this when we did talk about, well, we do talk about gravitational force. So a vector field takes a point in space and returns a vector. I didn't spell that right. Let me just kind of get back. Okay. So we're going to take a point, and then we're going to return this vector. Now, when it comes to vector fields in physics and the AP Physics kind of area, there are two main vector fields that are studied. One here in AP Physics 1 and one in AP Physics 2. In AP Physics 2, because the focus is more modern, it's the electromagnetic field. And then here in Physics 1, we'll talk about the gravitational field again. Okay, we talked briefly about this at the beginning of the last unit, but we're going to go a little bit deeper into this. Now, what happens is you'll notice that there's a correlation between the two. Both of these laws are what we call inverse square laws. And this is going to pop up again later. Okay, and once you see the equation, you'll see why it's called an inverse square law. It just means that it varies inversely to the square of the distance between them. Now, what does that really mean about the magnitude? Okay, so the magnitude of the force decreases quick. Okay, and so if I just kind of talk about, a central object, right, and I have one here, another object here, and I have another object here. So the force between these two is going to be much greater than the force between these two. So if I was 2, this 1. So like F1 will be greater than F2 because the distance that 1 is away is less than, not greater than, sorry, is less than that of the distance that 2 is away. Okay, and this holds true for electromagnetic force as well as gravitational force. Okay, so remember, the gravitational field is always down. It's always pointing towards the center, and it has a value of 10 newtons per kilogram. Okay, we know this also as 9.81 newtons per kilogram. And again, so what this means is that a 1 kilogram object that sits in the field around Earth will experience 10 newtons or 9.81 newtons worth of force. Okay, and one thing that we do state is that near the surface of the planet, the gravitational field is constant. And we can do a quick little example or a quick little calculation to show you how this field is constant through a method called factors of change. Okay, and so in this little box describes how to do the process of factors of change. And so what you're going to do is you're going to have an equation. You're going to substitute 1, like the number 1, for values that remain constant. Plug in the factor of change for anything that changes. Right. So for example, how many times greater or how many times smaller that factor is compared to the other one. And then you're going to determine the factor of change for what you're looking for. So basically, you're going to solve, right, for what you're trying to figure out is bigger or less. Okay, and so here's an example, right? So this says prove that the gravitational field is approximately constant by comparing the G value at Denver to the G value at Miami. Okay, and Miami is located at sea level, which is approximately 6,300 kilometers. And Denver is at a mile high, which is 63 6,301.6 kilometers. Okay, that's why Denver is called the Mile High City, is because it sits 5,280 feet up. All right, so so what happens is, a little preview of an upcoming equation. So we find that the gravitational force is actually this equation. So G m1 m2 over d squared. So G is a constant. You got mass 1, mass 2, and the distance squared. Okay. So and what happens is that mass 1 would be like the object. Mass 2 would be the Earth. Okay. And then the d is the distance between the two objects, right? And so what happens is if the object is on the Earth, the distance would be, right, essentially the radius of the location, okay? And so here's how it works. So what we're going to do is compare Denver to Miami, right? So we're going to look at what is really the difference between the two. And so we need to find what is the ratio of the distance that Denver is away versus Miami. And so we're going to do 6,301.6 kilometers divided by 6,300 kilometers. Okay, and we're going to get kind of the ratio that these distances are apart, or these radii are apart. And so it's going to be a value of 1.0003. Okay, I'm going to carry that far out just so you can see how this method works, because that's just one. Okay, and so what we're going to do is we're going to look at the gravitational force, right? And we're going to try to find the factor from this equation here that compares Denver to Miami. So G is a constant, so I'm going to plug in 1. That's not going to change. We're going to do the same object, right, in Miami that we're going to do in Denver. So we're going to plug that mass as 1. The Earth also doesn't change. And then I'm going to take this ratio I found, because this is the factor that changes, right? So what is the difference, the ratio of those two distances? And so then I'm just going to kind of say the number that comes out of this is my factor of change. So this is the number that I'm looking for. And so I'm going to do essentially 1 divided by 1.003 squared. And I'm going to get 0.9994. And then if I put that into a percentage, right, multiply this by 100, I'm going to get it's 99.94% of it, right? So what does that mean? That's a 0.06% difference between the two. And that's basically constant. So when we talk about the gravitational force is constant, that's what we're talking about. There's a less than a 1% difference between sea level in Miami than Denver, which is one of the highest points here in the United States. Okay, so from here on out, we're gonna continue to work on our, build all the way up to circular motion. We're gonna still do some gravitational field type scenarios as we go from here.